Hey guys, sorry I missed today. I had not really planned on it. Um, I had to go to an orientation that was just going to be an hour long, and had hoped to just kind of take off for that brief amount of time that I need to be gone, but it didn't work out that way. So honestly, it was kind of one of those situations where it was easier for me to take the whole day than to take just a partial day. So that's what I did. So I hope that you guys are having a good day. What I want to do is I want to go through your homework from last night, and then going to teach you guys how to solve a certain type of exponential equations. I'll talk more about that in just a minute. But anyways, get out your homework from last night. We're going to go through these 7 problems that you had as your assignment, and then jump right in. So hopefully the note sheet has made it to you for today. That way, when I'm done with this, we can jump straight in to your notes for tonight. It's Friday. I hope that you guys have a great weekend, and I will obviously be back on Monday. This again was not really the way I had planned it, but it's just the way kind of it worked out. So I've left 2 of these blank that I'm just going to talk through with you. Number 1, 2, and 3 should have been pretty easily. Again, don't get caught up on the a value that's out front. What I mean here is like for this particular problem, that a value is that 1/2. Don't try to multiply that by the 5. It wouldn't matter anyways. When we talk about whether or not it's exponential growth or exponential decay, we're specifically talking about the base of the exponent. So on number 1, the base of the exponent is 5. That's definitely growth. On number 2, the base of the exponent is 6/5. That's greater than 1. I know it's a fraction, but it's greater than 1, so it's also exponential growth. On number 3, the base of your exponent is 3/8. Okay, 3/8 is obviously less than 1, so that's going to be decay. And your graphs didn't have to be anything spectacular. I just wanted you to remember that exponentials start, or growth start flat and go up, where exponential decays start by going down and then they flatten out. So just be familiar with those. Okay, number 4 didn't have a lot going on there. The base of your exponent, of course, was 4/5 x, so that's my what we call parent function. So the only thing that was going on here was that +2, and that was happening in the exponent part. So we talked about yesterday how that's kind of considered like it's on the inside, and on the inside, when we're adding and subtracting something, that's horizontal shift. Horizontal shift. So since it looks like it's a minus or a +2, we talked about how a horizontal shift is always the opposite. So since that looks like a +2, it's actually a -2 horizontal shift, which means it shifts left 2. All right, so I want to do number 5 with you. So first thing, I want you to recognize that the base of your exponent is right there, that 2. That is my parent function, okay? F of x equals 2 to the x power. That's my parent function. Anything that is not 2 to the x power is considered, like we talked about yesterday, a transformation. So let's start out here. We've got this negative. What's that negative telling me? When a is negative, this thing has to reflect over the x-axis. That's my first transformation. But then we look at that a value and it's a 3. 3 is obviously greater than 1. So that's going to make this a vertical. It's going to yank it up and make it a vertical stretch. Okay, that's all of a. Now we go out here to this -1 that's up in the exponent spot, so it's inside. So again, what we said is we know then that's horizontal shift. And of course, since it says -1, we know that that really means a +1 horizontal shift. So that means a +1 horizontal shift. It shifts to the right 1. And then, of course, this last thing we have is outside. We're adding 7. Outside represents vertical shift, and it is what it is. So this thing is going to shift up 7. Now, I know that this is not one of the questions, but like we did yesterday in the notes, please remember the association between the vertical shift right here and the asymptote. Remember, if you had no transformation, we said that the asymptote for a exponential function is always y equals 0. But if there's vertical shift, whether it's up or whether it's down, if there's vertical shift, what that does is it changes your asymptote. So this one changes to y equals 7. Okay? Now, we didn't do that on the other one. Didn't need to because it had no vertical shift. See, it has that horizontal shift, but it didn't go up or down. So therefore, it had no asymptote. Okay? Now, I went ahead and graphed this one for you using my calculator. I want you to notice it does have vertical shift. It went down 7. So as you can see, the only red line I have here is the horizontal asymptote, which is y equals negative 7 because it dropped down 7. Then, of course, I just typed the whole thing into y equals and found some points. I found the y-intercept, which I thought was important because it's right here, 0, negative 6.889. And I found a couple of other good ones, as you can see listed. And if you graphed it, you'll find those as well. Now, all those questions that we answered yesterday should be pretty easy. It never stops going left, never stops going right, so my domain is negative infinity to positive infinity. However, the range, it cannot go below this ceiling right here. That's it. That's as far as you can go. So negative 7 is the lowest value, but it goes up forever, so therefore my range is positive infinity. Again, in behavior, as x goes off to the right, you can tell your graph is going up, so we define up as infinity. And as x is going off to the left, you can tell that your y is approaching that ceiling. It's approaching that asymptote, so it's approaching negative 7. So there you have it. But I want to do one graph with you just so we can give this a little bit more time just to make sure that we're all on the same page. I hope that you notice right off the bat, and we're going to see this too when we graph it, but see that vertical shift? This thing is going to go down 3. So my asymptote is going to be right here at negative 3. And I'm going to prove it to you in just a second. But my horizontal asymptote is y equals negative 3. Now let me prove that to you. Let's go to our graph. And let's type this thing in. We've got, and I'm going to go ahead and type it just like they have it. Alpha y equal, in parentheses, I'm going to have 1/2. Always type it the way they type it. That way there's no chance you make a mistake. Then I'm going to raise that to the x plus 4 power. And then I'm going to scroll down here and put my minus 3. Now look at the graph. Sure enough, to see how it lowered your asymptote down here to this negative 3? Now I know it looks like it's right on top of it, but remember, your calculator only has so many pixels. So obviously we're not able to see exactly what that is. So let's go look on our table. Second graph. And sure enough, we got some nasty decimals here. So I'm going to type these in, see exactly what they are. But as you can see here, your y-intercept is 0, obviously. And then it's negative 47 over 16. Negative 47 over 16 is negative 2.9375. See how close that is to negative 3? Doesn't quite get there, but it's pretty close. Let me go back to my table, see if we have any good points. Oh yeah, we got some good ones. Here they are. I'm going to do all the ones that I can. So that's negative 7, and then positive 1, 2, 3, 4, 5. We've got negative 6, positive 1. We've got negative 5, negative 1. And one more good point, negative 4, negative 2. So let's go back now. And you're all following along here. Sure enough, there's my points that I was able to find really easily with my graphing calculator. So let's just draw our graph to go through all those points, but then to never cross my asymptote. Voila, there's my graph for this particular exponential function. So let's name all these things that we know. Oh, I forgot to write this. It was negative 2 point, what was it? Negative 2.9375. So let me go write that real quick. Negative 2.9375. If you put negative 47 over 16, that's fine. It's just you don't know what that is, probably. But you know what negative 2.9375 is. Okay, so my domain. It never stops going left. It never stops going right. Exponential functions will always have an unlimited domain. But your range will not go below what value? Negative 3. It'll go up forever. Now, a lot of people have a hard time with that because, see, this is definitely decay. So it's going down. Why can I say then that it goes up to positive infinity? Well, think about it as far as just the y-axis. Where will it go on the y-axis? Will it go down? No, down is negative infinity. It won't go down here, but it will go up because all these y values appear positive. So that's why it looks, I know it's decay, but it's still, the range is from negative 3 up to positive infinity. Again, the end behavior, very simple. As x goes off to the right, look, what is y approaching? It's approaching your asymptote, negative 3. But as x goes off to the left, what's y approaching? Positive infinity. So there you have it. Really, really simple stuff that we did yesterday. Hopefully you guys were able to do all those and do them correctly. If you didn't, hopefully you've taken the time to write this down as we've done it. It's been up there quite a while, so really there shouldn't be a reason you don't have this done. Okay, so that is it for last night's assignment. Pretty easy assignment. So far, we've done inverses and we've done exponential functions. We've talked about their transformations. So we've done pretty good. Now we're going to move in to solving exponential equations. Now let me explain a couple things here. One, there's going to be a couple of good ways to solve exponential equations. What we're doing today is we're doing the first type. Now, I'm going to be honest. The first type will end up not being your favorite type. It's useful when your problems are written or done a specific way, but there's actually an even better way to solve exponential equations that we will do soon, okay? Very soon. So there are multiple ways to solve exponential equations. So today, we're going to do the ones where, as you see here, type 1, equations that have a common base. Again, the first thing I want you to understand is these are called exponential equations. Why? Because there is a variable in the exponent spot, and we've got to solve for that variable. So when we have exponential equations that either have a common base or in a situation where we can create a common base, it's a pretty simple method. One, we're going to use the properties of exponents to simplify each side of the equation. Obviously, some of these we won't have to simplify at all, but others we'll use our properties of exponents to simplify. So let me quickly remind you guys of those properties of exponents. Here they were. Remember, when we are multiplying, whoops, did not mean to do that. When we're multiplying and our x's are the same. So let's say we have 5 to the second. Let's use variables instead. If we have x to the second times x to the third, remember the rule? Your base stays the same, and we add our exponents. So this becomes x to the fifth. I think you remember that. But if we're dividing, remember the rule? If I have x to the fifth divided by x to the second, remember the rule? Your base stays the same, but you subtract. 5 minus 2 gives me x to the third. And then, of course, there's some other properties like the power to the power property, and we'll talk about those. But I'm trying to remind you guys of what those properties of exponents are. We're going to use those to simplify each side. Then, two, we're going to rewrite the equation to make sure that both sides have the same base. And as soon as they have the same base, we're going to do this thing where we drop off the bases and then we're going to just set the exponents equal to each other and solve. So for example, look at number 1. Is there multiple things on the left side that we need to combine? No, not on the right either. So we don't actually have to do step 1 and then step 2. Look, they already have the same base. If they already have the same base, we don't have to do step 2 either. We move straight to step 3. If your bases are the same, you literally let them cancel. You drop off your bases, and then you take the exponents and you simply set them equal to each other and you solve. So how would I solve this problem? You'd subtract 1. So literally 9 minus 1 equals 8. The solution to this exponential equation is x equals 8. Now, I know you're looking at that problem and you're like, there's no way it can be that easy. It is, okay? If there's nothing to simplify and the bases are already the same, it really is that easy, okay? Look over here at number 2. You see the same thing. There's nothing to simplify. The bases are literally both the same. So we're going to drop off the bases and we'll take those exponents, 4n plus 5 and n minus 7, and we'll set those equal to each other and we'll solve. Now, the only thing that's harder about this is just the process of solving. So remember, I always like to start with the variables. So I've got 4n and positive n on opposite sides. I always like to move the smaller one. So I'm going to subtract n. 4n minus n is 3n. So 3n plus 5 equals negative 7. Then I'm going to go through my process of getting n alone. So I'm going to subtract 5. Negative 7 minus 5 is negative 12. And then finally, I'm going to divide by 3. What's negative 12 divided by 3? That's negative 4. So literally, n equals negative 4. So on problems like number 1 and 2, they really are that simple. Now they'll get harder. For example, look at number 3. Yeah, I know that all of my bases are the same, but I want you to look at this left side. It's got 2 things that are doing what? They're multiplying. Well, if they're multiplying, what's my rule? When I am multiplying and my bases are the same, what's the rule? Well, hopefully you remember, the base stays the same and we add our exponents. Now we'll come back to that in just a second. This side's already done. So here it is. What is k plus k? Well, that's 2k. So what we really have here is 2k plus 2 up there on top. So now we have done step 1 where we got anything on the same side that needs to be combined. We got them together. And sure enough, once again, since my bases are the same, we're going to drop off those bases and we're going to set the 2k plus 2 equal to the 5k minus 1. So once again, very similar to the last problem, I'm going to subtract this 2k from 5k. I like to move the smaller one. That's 2 equals 5k minus 2k is 3k minus 1. I'm going to add 1. What's 2 plus 1? 3. So 3 equals 3k. Kind of running out of space here. Let me move this. Actually, I'm just going to make it a little smaller. And then, of course, lastly, to get k alone, I'm going to divide by 3. 3 divided by 3 equals 1. So k equals 1. And now I am done. Pretty simple, right? I hope that you agree. It's not that hard. All right. So we're going to keep on moving. I'm going to jump around a little bit. So let's go to number 5. Now we're going to deal with a problem that is a little different because as you notice here, right off the bat, these equations don't have the same base. See, this one has a base of 6. This one technically doesn't have an exponent. I mean, it does. It's technically 36 to the first power. But those bases are not the same. Okay, one's a 6 and one's a 36. So this is where you have to start using your brain a little bit. Can I create this bigger one to have the same base as the smaller one? Well, sure, I can rewrite 36 to have a base of 6. Does anybody know how? Hopefully you said or thought 6 squared, right? What is 6 squared? Well, it's 36. So now we've created this. Even though it started out not having the same base, we created that 36 to have the same base. And now we can, once again, drop off our bases and we can solve. 2x minus 10 equals 2. I'm going to add 10. Then I'm going to divide by 2. So x equals 6. Okay? And that's really all there is to it. It's actually not that bad. Let's cruise over here to number 6. Again, look, we've got a base of 2 and we've got a base of 8. Okay? Can I create 8 to have a base of 2? Grab your calculators and try it. Okay, if I went back to my calculator and I went, okay, 2 times 2, does that equal 8? No. Times 2 again. Does that equal 8? Sure enough, 2 times 2 times 2, or how else do we describe that? 2 cubed equals 8. So sure enough, I can create 8 to be 2 cubed. And now all of a sudden, don't they have the same base? Well, if they have the same base, drop the bases and let's solve. So we have p minus 7 equals 3. What do I do from here? Add the 7. So p equals 10. And that's it. That's how you do it. So sometimes when they don't have the same base, we create them to have the same base. Let's keep cruising and see if y'all can do this. This one's a little harder. Now, I know this is 7, and I know this is 1 over 7. And 1 over 7 is technically smaller, but it's also a fraction. Can anybody think of how maybe I could rewrite this 1 over 7 to make it have a base of 7? It is something we've talked about. What pushed that 7 to the denominator? What would we be able to do that would allow us to move that 7 to the denominator? Well, hopefully you remember the idea of negative exponents. Negative exponents allows a number to move from the numerator to the denominator. Remember, we change its position, and that changes that exponent to be positive. Well, remember, 7 on the bottom is just 7 to the first power. So I can move that back to the top and make it 7 to the negative first. That's another way we can rewrite 1 over 7 to make it have a base of 7. 7 to the negative first power. And now that my bases are the same, I drop my bases, and I take what's remaining in the exponent spot, 4x plus 11, and I set it equal to negative 1. So let's solve it. I'm going to subtract 11. So 4x will equal negative 12. Then I'm going to divide by 4. So x equals negative 3. Okay? Hopefully that makes sense to you. It's not too bad. Let's look at number 9. Number 9, I have a base of 27, and I have a base of 3. So 3 is my smallest one. So my mindset is, can I make 27 have a base of 3? Well, let's go see. 3 times 3 is 9. That's not it. Times 3, 27. So 1, 2, 3. 3 to the third power gives me 27. Now don't forget, what was already here in the exponent spot? 2x plus 6. That can't just disappear. Okay, now I rewrote 27 as 3 to the third, so that 3 is in the exponent spot, but there was already a 2x plus 7 there. Now, the other side's good to go. Now that I have the bases, both 3, I'm going to drop those bases off, and I'm going to solve. So here's how we do it. On that left side, let's go ahead and distribute. What is 3 times 2x? 6x. What is 3 times positive 6? Positive 18. So 6x plus 18 equals 2x. So I'm going to move this 2x over here by subtracting it. So 4x plus 18 equals nothing. I'm going to subtract 18, and then I'm going to divide by 4. Negative 18 divided by 4 is going to give me negative 4.5. So what you think about that? That wasn't too bad, was it? Again, that one might be a little trickier for you, but we created those bases to be the same. So we created 27 to be 3 cubed. All right, let's keep on rolling along. Let's look at number 11 here. All right, so here I have the bases of 125 and 25. Well, 25 is my smaller one. Let's see if we can make 125 have a base of 25. So 25 squared means 25 times 25. Does that equal 125? No, that's way too big. So I actually can't create 125 to have a base of 25. Now, here's my next question then. Can I change these both where they would have equivalent bases? Well, let's look. What I know y'all are familiar with 25. Isn't 25 5 squared? It is. 5 squared is 25. Well, if I multiply that one more time by 5, look what you get. You get 125. So we can make both 125 and 25 have a base of 5. 125 is 5 cubed. Now again, don't forget you still have that y up there, so it stays there, and it just multiplies by 3, so that's going to be 5 to the 3y. And over here, you can rewrite 25 as 5 squared. So again, now that I've got my bases the same, I drop off those bases, and I take 3y and set it equal to 2. To solve for y, I'm going to divide by 3, so literally y equals 2/3. Yeah, that's pretty tricky, right? Sometimes you don't have to change any base. Sometimes you have to change one base. Sometimes you have to change both bases, like we did right there. Let's go over here to number 14. This one's pretty tricky. This one has a base of 81. This has a base of 1/3. That's clearly the one I want you to think about first, because as you can see here, that 3 is the only way it can be written is to have a base of 3. And remember, how do we allow that fraction with that 3 in the denominator? How do we allow it to come back up to the top where you have a 3? Remember, that's where the negative exponent comes in. And since it's just a 3, that's, remember, 3 to the first. So this is going to change to 3 to the negative first. Now don't forget, you already had the 2x up there. So that's negative 1 times 2x. Now let's check 81 and see if we can make 81 have a base of 3. 3 times 3, 9, times 3, 27, times 3, 81. There it is. 1, 2, 3, 4. 3 to the 4th power. 3 to the 4th power gives me that 81. Now don't forget, you had that 2x plus 5 up there, so it needs to stay up there. But now that we've created our bases to be the same, we can multiply 4 by 2x plus 5. 4 times 2x is 8x. 4 times positive 5 is positive 20. And then on the right side, negative 1 times 2x is negative 2x. Now to solve this one, I'm going to add 2x over here to this 8x. So 10x plus 20 equals 0. I'm going to subtract 20. 0 minus 20 is negative 20. Then I'm going to divide by 10. So x equals -2. What do you think about that? Hopefully you understand it and it's not that difficult. Okay? All right, moving along. We're going to do number 17 and then we're going to do number 19. And I think that will cover you as far as what you need to know for your homework tonight. So first thing I need you to see is ignore the 64 for the minute, okay? Right now, let's focus on getting this together. Remember, when you have that 4 times 4 to the 4x, technically what you have here is the same base, and those are being multiplied. So remember what you do when you're multiplying, the base is the same? You add your exponents. Your base stays the same, and you add your exponents. Well, here's where people get thrown off on this. Technically, what is the exponent of this 4? Technically, it's 4 to the first. So if I want to combine these, I've got to take those exponents and add them. So that will be 1 plus 4x. And I can't combine those because one has no variable, the other has a variable. So now that we have this base 4, let's see if we can make 64 also have a base of 4. So here we go. 4 times 4 is 16 times 4 is 64. There it is. So 4 times 4 times 4. 4 cubed gives me 64. So I sure enough can change this to be 4 cubed. Now on the other side, we still have 4 to the 1 plus 4x. Since these bases are the same, they cancel, and we take the 3 and set it equal to the 1 plus 4x, and we solve. So I subtract this 1, that's a 2, equals 4 times x. I divide by this 4. 2 divided by 4, guys, is 1/2. So x equals 1/2, or 0.5 if you prefer. Okay, last one. Let's try to knock this thing out. This one's pretty tough. I'm going to ignore the 1 over 7 for a second. Actually, you know what? I'm not. Remember, that's 7 to the first in the denominator. As you can see here, clearly we're going to make our base to be a 7. So that's going to be 7 to what power, guys? Hopefully you see that. It's in the denominator. To make it come up, we make it -1. 49. Guys, how do I make 49 have a base of 7? Well, that's 7 squared. But don't forget, you already had that x minus 5 up there. We'll come to that in a second. And that's being multiplied by 7 to the x minus 9. Now remember, we need to get this all together. You are multiplying, see, and your bases are the same. So we can get those together by adding your exponents. So what are my exponents? Well, this one, 2 times x minus 5, that's 2 times x, that's 2x. And 2 times -5, that's -10. And you're going to add the x plus 9. So what we have here is we have 7 to the -1st equals 7 to the 2x plus 1x is 3x. And -10 plus 9 is -1. So there we have it. We've gotten it all together. We're now going to let our bases cancel. And we're going to be left with -1 equals 3x minus 1. So to finish that thing off, we're going to add 1. -1 plus 1 is 0. And then we're going to divide by 3. So 0 divided by anything is 0. So sure enough, x equals 0. So maybe this is a little challenging, and that's okay, all right? You can handle this. It's not as hard as we sometimes make this stuff. Remember, the whole idea behind this is you have to have same bases on both sides of your equal sign. That way you can let them cancel and then solve. We've done several examples, and they are enough examples to get you through your homework, which is number 2 through 20 even on the worksheet that you either already have gotten or it should be headed your way right now. All right, this is a 35-minute video, so you still have about 11 minutes left in class, 10 solid minutes to get some stuff done. So I expect that you use the time wisely and try to finish these up 10 problems so you won't have any homework over the weekend. Have a good one.